In this video, we'll take a quick look at Newton's law of gravitation. This will be a relatively short sequence. Actually, there will only be one video in this sequence. This will be our introduction to gravity methods in geophysics. I expect this will probably be a review from high school physics, but nonetheless, we'll take a look at it. Our understanding of how we state the magnitude and direction of Newton's gravity force within Newton's law of gravitation will depend on your understanding of basic vectors. So go back and take a look at that video if you're not sure what a vector is or how to describe it. So Newton's law of gravitation looks at the attractive gravity force between two masses. So let's suppose that we have one mass here, call it M1, and it's located at position given by the position vector R1. And then we have a second mass over here, call it M2, and that's at a position given by the position vector R2. Now, Newton's law of gravitation states a few things that guide us towards writing out the mathematical equation that represents Newton's law of gravitation. So, if we have a gravity force between these two, first of all, it says that F, the force, the gravity, the magnitude here, is proportional to the mass of the first object. It's also proportional to the mass of the second object, and it's inversely proportional to the distance between them. So I'll write 1 over r squared. So it's directly proportional to m1 and m2, and it's also inversely proportional to r squared. So r is the distance between the two objects, so that means the further they are apart, the smaller the force is. And that makes intuitive sense. And Newton's law states that this force is always attractive. So M1 pulls M2 towards it, and vice versa. M1 is pulled towards M2. So the force between them is equal, and the force of 2 on 1 is equal and opposite in magnitude, opposite in direction to the force of 2 on 1. And that's because of Newton's law that forces have to be equal and opposite. So how can we actually express that? So first, it helps to draw a vector between the two. So I'll draw this vector, which gives us the direction from 1 to 2. So I'm going to call this vector R12. And R12 is equal to R2 minus R1. So that gives us the distance from 1 to 2 and the direction from 1 to 2. As part of writing out the expression for the force between them, it will be useful to have the unit vector on that direction as well. So I'll call this one R12 hat, which is the unit vector. Now, Newton's law of gravitation states that the force between them is attractive, so that means the force of 1 on 2, so the force felt by 2 due to 1, must point back towards M1. So this force here I'll call this F21. So the force felt by 2 due to 1 must be equal to. So now we'll work through these proportionalities. So because it's proportional to M1 and M2, in the numerator we must have M1 and M2. It's inversely proportional to R squared. So in the denominator, I'll put the magnitude of R12 squared. And it's attractive, so it's on the line given by the unit vector R12. But it goes from 2 back to 1, whereas R12 points from 1 to 2. So I'll put a negative sign out front. So this gives us the basic form, including all of the variables that we need to express the law. This proportionality here doesn't tell us anything about the magnitude, so it leaves out a constant of proportionality. So in Newton's law of gravitation, we call that constant of proportionality G. G has a value of approximately 6.674 times 10 to the minus 11 newtons meters squared per kilogram squared. And that is the recommended value as of 2014 for G. We also know from Newton's second law that this F is equal to m2 times the acceleration of 2. So I can say that F equals ma, m2 times a21. So this says F equals ma. This a21 is the component of the acceleration of m2 due to particle 1 here. So if we have lots of particles around, then m2 might have components of acceleration due to all of the other particles as well. But in this case where we just have the 2 particles, then this is the entire acceleration of particle 2. So from this we can work out that a21 is equal to negative g times m1 over r12 squared, and then the direction is given by this unit vector here and the negative sign. So that's the acceleration of 2 towards 1. In gravity surveys, what we're interested in is the acceleration of objects towards the Earth. So at the surface of the Earth, we have that m1, the object that's doing the attracting, is the Earth. So that's the mass of the Earth. And the radius here, if we're at the surface of the Earth, is the radius of the Earth. So I can say that G at the surface of the Earth is equal to negative capital G, constant of gravitation, times the mass of the Earth divided by the radius of the Earth squared times a unit vector r hat, which points outward from the center of the Earth towards the point at which we're interested in, G. The measurement of G is, of course, the object of gravimetric surveys, so we need to measure very small changes in it near the surface of the Earth. But in general, for rough calculations, G is approximately, on average, equal to 9.81 meters per second squared at the surface of the Earth. And so that's a global average, obviously, as we'll be finding out through this course, part of this course about gravity surveys, that varies over the surface of the Earth due to latitude, elevation, local anomalies, and so on. So that's what we're going to be learning about in this course on the geophysics of gravity surveys, but in general, that's an average value. Okay, so that concludes the basic introduction to Newton's law of gravitation. Of course, as a final note, Newton's law of gravitation is an empirical law. It describes the effects of gravity, but it doesn't explain its origin. So to explain the origin of gravity, we need modern physics theories such as general relativity to actually understand where does that force come from. This one simply says there is this attractive force that we call gravity, and this is how we predict its magnitude. And this g constant we have a relatively accurate measure of. Okay, so that concludes the video on Newton's law of gravitation. Thank you.